In this video, I wanted to do a few examples of solving quadratic equations using the quadratic formula and using the discriminant to determine the types of solutions you're going to get. So let's start off with a few examples. In class this week, we talked a lot about why the quadratic formula is true and the algebraic reasoning behind it, but we didn't really get into examples of actually how to do it and my recommendations. So that's kind of the main point of this one. Anyways, obviously we can always start by figuring out what are A, B, and C, and reminder that the quadratic equation needs to be set equal to 0 in order for the quadratic formula to work. Our first example here is already set to 0. We're good to go, and so the coefficients A, B, and C are just going to be the numbers on each term, where if there is a missing coefficient, that can always be treated as 1. And so basically in this case, A is going to be 1, B is going to be 3, and C is going to be 5. And we could plug all those things into the formula to get started. And as I said in class, usually what I like to do is do the math as I go. So in this case, the answers to our equation here will be negative b, which is 3, so negative 3, plus or minus a square root. And I like to do b squared as I go. So in this case, b is 3, b squared would be 9. And then it'd be minus 4 times a times c. And so a is 1, c is 5, So it'd be negative 4 times 1 is negative 4, negative 4 times 5 is negative 20. So in this case, I would have minus 20. And this would all be divided by 2 times a, which is 1, 2 times 1 is 2. So I kind of like to do it in 4 parts. What is negative b? What is b squared? What is minus 4ac? And what is 2a? Kind of plug all those 4 numbers in and then see what I'm working with. And as a reminder, the quantity on the inside of the square root is called the discriminant with the quadratic formula, the b squared minus 4ac. And a reminder that when it is negative, it will always produce a non-real answer, because the square root of negative, no real number has a square to be a negative, of course, because any number squared is a positive, any real number that is. But as we talked about in 7.7, there are numbers that do work with, within having a square be a negative, and that is by definition the imaginary unit. And a way that we can deal with this is, of course, we could actually do the math there. 9 minus 20 is going to be negative 11. And then I like to think about it as extracting the negative as I, because the square root of a negative 11 is not real, but the point of the imaginary number system is to provide an algebraic solution for situations where there is nothing real that actually works. And as we discussed in 7.7, there actually is a lot, even though we call them imaginary, it doesn't mean they're made up or fictional. They actually have a very real purpose in a lot of mathematics, physics, and so on. Anyways, so basically what we do is I like to think about it as I'm going to pull the negative out of the root. That is I, the square root of negative 1. Or you could even think about it as negative 1 times 11, the square root of 11, like that. Technically, the square root property that I just referenced does not work for negatives, but that idea can help us think about it. And then by definition, the square root of negative 1 becomes I. And the thing to remember about this is that when you're changing it to I, it's no longer going to be in the square root, but the 11 will still be within the square root. And so this would be I times root 11. Or you could write it as root 11 times I. The order that you write it doesn't matter. And another thing that I like to do when I'm finishing my answers here is, well, this is a pretty horrible expression because 11 is prime. We can't simplify that components. Each, involves fractions and all sorts of different components. But we could also write this as a standard complex number. Normally how we write complex numbers is the real component plus or minus the imaginary component. So we could actually split this fraction up since, we have a common denominator of 2 here. Basically, I'd have the real component, which is just the first part, negative 3/2. And then it would be plus or minus the second part, which is the square root of 11 over 2. And usually, we write the I on the outside kind of like this. And this is how I would write my answers in these sort of scenarios, by, writing it as a real component and an imaginary component in that order. And anyways, in this case, we can still come up with the solution to our quadratic equation even when we can't factor it or do anything else. So, basically all quadratic equations have solutions. Sometimes they might be pretty ugly though, and that's kind of what we get in this particular case. So let's do a couple more. And again, you can always think about how could I factor the polynomial as an alternative pathway to solving these if you think it's simpler. But in some cases, when we're dealing with prime polynomials, you can't factor it. So there's no option other than quadratic formula. So let's just continue practicing with the quadratic formula as we go. So let's do the second example over here. And again, what I like to do is first set it up, plug in the numbers, and then think about the discriminant. So here, negative b is negative 6. So since it's going to be a negative, this is another thing really easy to forget. Since b is the entire coefficient including negativity, negative b would be a double negative 6 because it's already negative. So that would be positive 6. So what you can kind of remember is change the sign on b. That's always going to go out front. And then it will always be plus or minus that same chain. B squared, negative 6 squared is 36. B squared should always be positive because remember you're squaring a negative, which will become positive. And then minus 4 times a times c. So we can always obviously use a calculator for individual steps if they're, in this case, I'm supposed to do 4 times negative 3 times 24. Might be better just to do a calculator on that one. And in this case, I would have negative 4 times negative 3 times 24. And that's going to be plus 288 right there. And that would all be divided by 2 times a. 2 times negative 3 is negative 6. And again, before I simplify, I like to think about the discriminant. Here, the discriminant is going to be 288 plus 36, which is 324. And again, here it's positive. When the discriminant is positive, that means we're going to get real solutions, 2 real solutions. And whether or not they're going to be rational or irrational depends on whether this number is a perfect square. Now, you might not have your perfect squares memorized in terms of 324. Obviously, we could always check with a calculator, but that is indeed 18 squared. And in that case, we're going to get 2 very real solutions. So here we're going to have 6 plus or minus the square root of 324, which is 18 over negative 6. And basically in this case, all the numbers, all the roots are gone. There's no I, there's nothing crazy going on, just normal math here. And I'm going to end up with 2 solutions. 6 plus 18 is 24 over negative 6, which is negative 4. And then 6 minus 18 is negative 12 over negative 6 is positive 2. And I end up with 2 real solutions, 2 and negative 4. And we would have gotten those same answers had we just used factoring. And this is another thing that you can know. If you're ever wondering, how do I know if a polynomial, if a quadratic can be factored or not, it always comes down to what are the types of answers you get. And when you get very, rational answers, whole numbers, that means that this should have had a very easy way to factor based on, because you would have gotten the same solution no matter what way you would have done it. Which is an idea that's expressed if you guys ever take pre-calc or college algebra. The next chain in this course, you would talk about what's called the factor theorem, and there's a correlation between the factors of a polynomial and the roots given by its zeros. And anyways, essentially this polynomial would have factored as x minus 2 times x plus 4. And you might have noticed that there was a common factor of 3, and if we would have, or even negative 3, if you would have factored out negative 3, would have made this problem a lot easier. We could have gotten that answer more straightforward. But as you can probably agree, the quadratic formula is still relatively easy. It takes a little bit of math, but if you're kind of catching my drift, what I always recommend doing is first plug in the numbers, second, simplify the discriminant, figure out what's going on with your radical. Then once the radical has been simplified, we can progress further. I'll do a few more examples in the next video.